Okay, good afternoon, everybody. This is Mike Odell from Penn, Ohio. We're excited to have you with us to go over Back to the Future, or the past, or the basics, with a joint session between the Penn, Ohio chapter, the Rocky Mountain chapter, with Deanna Linton from Charter Communications, and the Chattahoochee chapter with Lynn Newsom from Broadband International. So we'll give it just another minute to let a few more folks join, and we'll go ahead and get started. Just a couple of clarification points or notes for today's session. If you do have questions, the audio is muted for the participants. So if you do have questions, please feel free to post them in the chat. We do have time scheduled at the end for questions and answers. So we'll be able to answer your questions, hopefully, when we get to the end of the presentation. So with that, we'll give it one more minute to see if any other folks join, and then we'll go ahead and shove off. Okay, let's go ahead and get started. Lynn, Deanna, thank you very much for joining me today to talk about amplifiers. I am extremely excited and very happy to have you both with us today.
Thank you.
Thank you.
Let's go ahead and Deanna, let's have you introduce yourself first.
Okay.
So tell us who you are and what you're working on these days.
Perfect. My background is in RF engineering. I have a degree in electrical engineering, and I came here to States around 10 years ago. Most of the time I have been working on defense, working in R&D groups, developing military-based product solutions. And then in 2020, I decided to join Charter to support plan evaluation and deployment of new equipment. I participate in development standards and guidance to help operations. I am currently working on amplifiers, is my main focus, and then I work on the extended spectrum amplifiers. And then I am actively a member of the Rocky Mountain chapter, and I also participate in a lot of the WIC events.
So I know that amplifiers is one area where you and I have had a lot of overlap between our two companies in the last couple of years, and have been cooperating in this space and functionally doing a lot of the same work. So I'm extremely happy to have you with us today to share your expertise and the work that you're doing at Charter. So thank you. Mr. Newsom, I know you've been around for a little while.
A long time, yeah. Well, good morning, everybody, or good afternoon, depending on where you're located today. And I'm very excited to be here with Deanna and with Mike. They're very experienced in the amplifier field, and excited to talk with them about the amplifiers and the HFC development. And I've been in the telecommunications for 43 years. 22 of those years was spent in the operating side of the business with various MSOs, and about 20 years in the manufacturing and or consulting side of the business, where we're developing amplifiers at Broadband International. And in the past 11 years, we've developed 223 different types of amplifiers, so that keeps us pretty busy. We're currently working on our 1.8 gig products and getting ready for a release on those products coming up soon. And we'll focus a little bit today on some of the 1.8 gig products and where we're going in the future. Thank you, Mike.
Thank you, Lynn. And for those of you that don't know me, my name is Mike Odell. I work for Comcast Corporation. I've started in the industry in the mid-90s as an installer with TCI Cablevision. Spent time in a bucket truck as a network maintenance technician and found my passion in the outside plant. These days, I work in Comcast corporate office centered in Philadelphia, focused on outside plant processes and technology. And I've been involved with the SCT chapter in Pittsburgh, the Penn, Ohio chapter, for about 20 years now, currently serving as the president again. Involved in a lot of the standards committees, the PNM Working Group 7, the Interface Practices Subcommittee, also in Working Group 5 and Working Group 8, and a graduate of the SCT Leadership Institute at Georgia Tech Scheller School of Business. I recently finished my stint as chair of the Cable Tech Games Committee after about 6 years there and handed off the reins of that to Justin Stiles from Charter. And my wife and I have 4 great children, a small farm in Northeast Ohio, and spend a lot of time in the gym with various athletic organizations. So that's us. Let's talk about amplifiers. So here's a question. Why are amplifiers still important? I thought, 10 years ago when I came to corporate at Comcast that amplifiers were going to go away. We were going to be all optical, or at the very least, node plus 0, with no amplifiers in our systems. So why are amplifiers still around? Why are they still important? Lynn, you want to take a swing at that one?
Well, guys, some of that's driven by cost, of course, and also the cost to put up and install a lot of fiber optics, which, we still put out a lot of fiber, but in my belief, amplifiers are going to be around for many years to come in the future, and we're only building better and better amplifiers today. So, 30 years ago, the amplifiers did not have the quality components that we're putting in those amps today. And we're going to have amplifiers around for a long time, in my opinion.
Deanna, why is it so important to have a better understanding of amplifiers today than it was maybe 10 years ago? Why does it matter?
I think it matters because, first of all, as we migrated to all digital signals, there is a lot of the old stuff that needs to be taken care of. It just looks different. And also, we're going to see in this presentation how we are getting limiting the TCP, which is incredibly important for the techs to be able to set the amplifier properly to deliver the high-speed services. And as we migrate to the 10G path, that's critical because the quality of the signal is what helps us provide that service.
Lynn and I were talking about this. For those of us that have been in the cable industry for a long time, we used to have very long cascades of tree and branch amplifier architectures with a lot of analog signals. And in order to provide quality analog video signals over long cascades of amplifiers, the proper alignment, meaning the input and drive levels and signal quality, were critical to that analog video delivery. So when we called this one Back to the Future, it's really some of the practices that we used 20, 30, 40 years ago to align very long cascades of amplifiers are still relevant today and probably as relevant or more so than they were 10, 15 years ago. So awesome stuff. Okay, our agenda today, we're gonna take turns with the topics. We're gonna start with amplifier evolution, move on to some of the key components of amplifiers, some of the characteristics or key factors of amplifiers, and then how to optimize amplifier performance. So starting us off, let's talk about amplifier evolution.
Sure.
Yana,
yeah.
You want to take us through this?
Let's do it. Yeah. So Back in the 1940s and 1950s, when television was becoming so popular, it was really difficult for those cities around outside the rural areas to get the signals. So some manufacturers are starting to develop some products to address this issue, and one of those products was amplifiers. So the first ones, that one of the first generations, they supported around 12 channels, and they consisted of a technology called twin lead wire, and they were based on tube amplifiers. This had a really simple circuit, and it was a bandwidth between 54 and 212 megahertz, and they only supported the downstream direction. By the early 1970s, the cable television upgraded those twin lead wire amplifiers to a higher technology, and it was called the solid state actives. And those was introduced to support higher bandwidths, up to 330 and then 450 megahertz. But then in the 70s, actives continued to evolve, and then the first standard package of semiconductors hybrids was introduced, and it was known as the SOT115J. This package was a big change on Amplifier Evolution because it helped operate a narrow band with short, not that many blocks, but it helps them to support two systems. So we introduced the upstream. These early two-way systems were from 5 to 30 megahertz, known as the sub-split or low split, and then from 54 to 450 on the downstream. But as demand for capacity increased in the 1990s, amplifiers with new technology were introduced to improve performance, and we increased parameters like frequency bandwidth, operational gain, and output levels to support high-speed internet services in longer distances. Then in the 2000s, with the introduction of digital compression, the signals advanced, and the semiconductor industry helped amplifiers to improve even more. These advancements in semiconductors have been allowing us, the vendors and the operators, to support higher reliable services, and it has created a next generation of amplifiers called smart amplifiers, which use everything electronic, and then they're going to have the auto alignment control. The next one. So as far as the configuration, on the forward path, some of the early hybrid amplifiers only have a push-pull stage, and for a brief period, around 450 to 550 megahertz amplifiers included a feed-forward stage. This technology had bandwidth limitations, and it never developed beyond 625 megahertz. Then, as the bandwidth and performance requirement increased, the push-pull circuit evolved to a pilot hybrid gain block, and introducing significant improvements on performance and higher output levels. The output stage today, as we know it, is a doubler block, and it uses a driver as a mid-stage block to support high output levels that are required to overcome the coax attenuation at the higher frequencies. Recently, a three-stage low noise amplifier has been introduced with low noise figure to support those even higher levels that we need, while increasing the performance as well. On the return configuration, the bandwidth has increased at a lower scale. So the stages started with 1, then the 1.2s, that as we know them today have 2 stages, and then as we go through ultra high split, it's going to require an extra stage.
I think this is important to spend a little bit of time on as you talk through the evolution of amplifiers into some of today's, even though they're higher quality components, having more stages of amplification to achieve the higher gain to support higher frequencies also brings with it some risk, right? I think we'll talk more about that later, but some of today's amplifiers have 4 forward gain stages and 2, to your point, in the future, maybe 3 return gain stages. So that poses some real challenges if they're not set up properly.
Right. Yeah, as we know, the hybrids are getting more complicated. Also, they are implementing stages in between the vendors, EQs and pads to be able to keep those stages happy. So at the output, we keep performance. So we need to be really diligent on understanding the amplifier and working with the vendors to make sure that we are setting them properly, and with the operations teams, because not all the HFCs are the same. So, and not all the amplifiers are the same. So we need to be careful on how we set those levels, and we will get in more detail on the next slides. On this one, we just wanted to highlight some the evolution of the semiconductor. So the first generation of the hybrids used on the output stage were BJT, or bipolar junction transistors, and these were used on analog amplifiers. The performance of these hybrids met the requirements needed back then, and they were used between 450, 550, and 750 megahertz amplifiers. In the 90s, the gas technology die was introduced, and it was able to support 860 amplifiers. Then the gas hybrids demonstrated questionable performance advantage versus the bipolar. So for the time, at that time, the die was kind of improved again in the early 2000s, and this started to be implemented in the 1 gig amplifiers. Then the next generation of the hybrid amplifiers was introduced in 2008 when GaN was adopted by the cable industry. These the power doubler gain blocks that provide delivery of high power and high frequency can also withstand really high temperatures. GaN-based amplifiers match the performance of the gas and even better the BJT, and they provide lower power consumption. Also, they perform way better. And this technology has been implemented mostly on the 1.2s and future 1.8 amplifiers. As we increase the bandwidth, amplifiers need to operate at higher frequencies. So we need to be really cognizant of amplifier TCP limitations, or total composite power, for unexpected performance. So we can see in this graph that in 1.2 amplifiers with 69 TCP, now we're pushing that to 75 in the 1.8s, and it's really close to the compression region of the semiconductor. For the 1.8 and the future 1.8, we need to be real careful on design, on following the design prints, or making sure that we know the dry levels of the amplifier, like where Mike is going to touch on later, to avoid operating these amplifiers in the crashing region.
So we see that difference between 69 total composite power and 75, and you're like, that's only 6 dB. Well, 6 dB is actually a lot when you're talking about total composite power, right?
Right.
So that's really important. Well, we talk a lot about total composite power today because it really is important to the overall performance and capability of the amplifiers. So good stuff.
Mm-hmm. On the upstream, there's not been a lot of changes. It's mostly following the progressive path of the forward. And as we can see, it's being marked by the same technologies. And we're now introducing ultra high split that is probably going to require the use of GaN technology.
Okay, so that's amplifiers over the years. Let's talk about some of the key components inside the amplifiers. So Lynn, I think between you and I, we can take this one and talk about passive plugins, diplex filters, and AGCs. First, let's talk about the passive plug-in components. As mentioned, some of our more modern amplifiers have a lot of stages and a lot of components in them. But in order for them to work properly, the passive plug-in components are very important. And when we talk about passive plugins, we immediately think about attenuators, cable equalizers, simulators, things like that. And we'll talk about each of those. But plugins come in a bunch of different shapes and sizes, and there are many points on the amplifier module itself to interact with these types of components. The amplifier schematics themselves are very important to understanding where the passive plug-in components are relative to other components in the amplifier itself. Things like the amplifier hybrids that Deanna just talked to us about, the GaN and the GaAs amplifier hybrids in the preamps. There are different places in between those amplifier stages in both the forward and the return path to condition the signal as it goes into those amplifier stages. And for that, the amplifier schematics are very, very important. This one's fairly generic, but it also tells you where your test points are. This particular schematic indicates a 30 dB down directional coupler test point before the diplex filter and before the forward pad and equalizer station. We'll also talk a little bit about directional couplers or splitters because they are important in both the forward and the return to direct the signal to the various ports on the amplifier according to the design. So passive plugins come in a bunch of different shapes, sizes, colors, depending on the generation and the model of amplifier that you use. But it is very important to know where they fit in the amplifier according to the schematics for your particular amplifiers. The schematics and users manuals, I'll continue to reiterate, they're very important. If you don't have a copy of the user manual for the amplifiers used in your area, I would highly recommend that you get them. They'll often include the performance specs for various parts and components that go in the amplifier. So this is a different schematic of an amplifier, and you can see where the bidirectional test points are relative to the diplexes and your passive plug-in components relative to your gain stages. But each of the passive plug-in components does have some very important specifications that you should understand. Things like flatness and what the bandwidth measurement is for that particular component. This is for a signal director or a splitter that would go in here. But you can see this one is rated, for a flatness of 0.3 dB out to 1.2 gigahertz or 1218 megahertz. Other passives made in years past to support other amplifier lines may not be rated out to your particular bandwidth. As I mentioned, some of the plugins like JXP attenuator pads, and we'll talk more about those later, we've been using JXP attenuator pads for decades and they haven't really changed. However, over the years, they may have been manufactured and rated only to perform up to 750 or 870 megahertz. So understanding the amplifier model that you use, what the correct passive plug-in components are, that's crucial information to get the best possible performance out of your amplifier. I put this in bright red because it's super important. Just because it fits in the slot doesn't make it the correct part. So let's talk about equalizers, simulators, and attenuators. Cable equalizers are intended to counteract the loss via attenuation of cable. So cable and the spacings between the amplifiers have attenuation. Now, attenuation is a function of frequency. The higher the frequency, the higher the attenuation. And that is not perfectly linear. in that relationship from frequency to loss or attenuation. So the cable equalizer isn't perfectly linear either. These are some actual cable equalizer signatures at higher and lower values. So in the top blue line here would represent about a 2 dB equalizer. And you can see it's relatively flat, but not perfectly flat. And then as you get into the higher values, like this 20 value equalizer here at the bottom, you can see there's actually a little bit of shape to it. Now that's intended to be the inverse of the, or the opposite of the shape of the cable to flatten that response based on attenuation. Similarly, cable simulators are intended to create loss that is in the same shape as the cable, so that the amplifiers can be more linear in their operation when it's short spacing between the amplifiers with a lot of loss, without a lot of loss. Attenuators are attenuators. They're flat loss across the entirety of their spectrum or their advertised bandwidth. Now, as I mentioned, this particular form factor, this JXP, has been around for a very, very long time. Not all of them, however, are rated out to 1.2 or 1.7 gigahertz. It's very important that you note in your user's manual or your specifications what the actual passband or flatness is. And I put this one here because this is a pretty standard JXP attenuator, but you can see that it is only rated out to 1 gigahertz or 1002 megahertz with respect to its loss and flatness. Any performance over 1 gigahertz may not be the desired response that you want from your attenuator. So it's important to match your amplifier models with the correct passive plug-in components. Now let's spend a little time with equalizers. Equalizers are also frequency matched to a specific bandwidth. In the table on the left, this is a cable equalizer chart for a 1.2 gigahertz amplifier. So all of the equalization values are measured across the entire spectrum from 1218 megahertz to 54 megahertz. Now, if our channel lineup only carries a 750 megahertz channel lineup through a 1.2 gigahertz amplifier, the equalization value of the equalizer may not match the amount of tilt that will be measured in our channel plan. So I have some blue arrows in these charts. Both of them are in 11 value equalizers. In the chart on the right, this is a 750 megahertz equalizer. So you can see in a 750 megahertz channel plan that only contains 117 channels, you can see that there is approximately 10 dB of equalization, the insertion loss at 750 equaling 1 dB to 11 dB of insertion loss at 54 megahertz. So you can see there's 10 dB of tilt from this 11 value equalizer. Now on those same channels with a 750 megahertz equalizer, you can see there's only about 7.7 dB of tilt associated with that equalizer, because the entire loss value of that equalizer is in fact 11 dB of equalization, but it's from 1.2 gigahertz to 54 megahertz. So when we install an 11 value equalizer into a 1.2 gigahertz amplifier that only has 750 megahertz of channel plan or active spectrum, there will be insertion loss of 4 dB on your highest channel. That's effectively taking away some of the operational gain of the amplifier. That's also very important to know when you're calculating the gains and losses of your amplifiers for setup reasons. So important to understand your equalization charts or the correct equalizers for your amplifier. Now, I'll go back to attenuators again and say just because it fits doesn't make it the correct part. There have been many variations of amplifiers or attenuators made for specific amplifiers over a long period of time. Many of them look the same. They might be slightly different in color or length, but they're not necessarily all of the same. So they can add shape to your signals and influence the overall frequency response if they are not rated for the actual bandwidth of your system. Other passive plugins can also be bandwidth limited, but can also be used in different amplifier series or models over time. So just some examples of directional couplers or splitters or other passives that can go into amplifiers. And again, they all do have insertion loss. It's important to know what their insertion loss is at what frequency as you're setting up and managing your amplifiers. So not a lot of folks take passive plugins seriously. They're, you know, $1's worth of plastic in most cases for attenuators, but that one little piece of plastic can significantly impact the overall performance of your system. So that's a little bit about passive plugins. Lynn, you want to run us through diplex filters?
Okay, sure. Thank you, Mike. So guys, first of all, let's establish what the diplex filters are designed to do. And we'll talk about the functions of the diplex filter. And basically, it's utilized to separate the upstream and the downstream, or the forward and the reverse RF signals inside of either an optical node or an amplifier. You can also see some diplex filters in the head end. If you have any direct feeds out of the head end, that typically requires a diplex filter to separate the forward and reverse path. And what the diplex filter does is it basically separates the forward and the reverse, and then the amplifier can then discretely amplify the reverse and then recombine it back through another diplex filter, and the same path with the forward signal, so that you separate those inside of the amplifier, but then they always get recombined when they go either to the input or the output of the amplifier. And so over the years, diplex filters have not had a standard footprint. Like as Mike mentioned, the JXP pad, it's been around forever. It has the same 3-pin spacing and dimensions that it's had from almost day one. And diplex filters do not fall into that category, because everybody makes a different style of diplex filter. Some of the early generation diplex filters were actually soldered directly to the board, and those were not field upgradable. Those had to be taken out, brought back into the factory or brought back into the shop. You had to remove 30 or 40 components, and then basically you're rebuilding the amplifier at that point in time. Each diplex filter would require 10 to 12 components, and in most cases you have either 2 diplex filters or 4 diplex filters per module. And modern day diplex filters, though, the diplex filters that have been used for the past 20 or 25 years are typically a plug-in diplex filter. And those are much easier to upgrade. And as we talk about the diplex filters, at the end, we'll also talk about how you upgrade a reverse amp and reverse split, because that is something many of you will be doing in the future. If you're currently at 4254, there's a good chance you may go to 85102 or to 204258. And those amplifiers can typically be changed out in the field, and we'll cover that in just a few minutes, okay? So guys, this is just a visual of some of the diplex filters that are actually in the market today, and this just shows you where you cannot take a Motorola diplex filter as an example and plug it into a Scientific Atlanta diplex filter location, because they just physically will not fit. All of these filters are good quality filters. They just have different footprints that each manufacturing company came up with years ago. All right, so guys, let's talk about the performance of the diplex filter. As Mike covered with the plug-in pads and equalizers and signal directors, those have a performance specification that you can see and measure in a lot of cases out in the field. If you put in a 5 dB pad, you expect to see 5 dB of attenuation. But the duplex filter does not work that way. So the manufacturer has to design a good quality duplex filter from day one. So we have to focus on a lot of the same issues that you would see in that JXP pad. Insertion loss is a very key factor there. We have to minimize that insertion loss. So typically, most duplex filters will have about 1 dB of insertion loss, because that insertion loss, if you have a duplex filter on the input of the amp and a duplex filter on the output of the amp, that insertion loss has to be considered in the overall gain of the amplifier. So if you have an amplifier with a 40 dB of operating gain, you have to have 2 dB more gain built into the amplifier just to overcome the insertion loss of the duplex filters. So we always try to keep those duplex filters at a very low insertion loss, 1 to 1.25 dB maximum. And I'll cover the out of band rejection and the crossover on the next slide. Of course, response is key as well. We need to have a very linear duplex filter so it doesn't start to add any peaks or dips in the response of the amplifier just because of the duplex filter. And of course, return loss is key in any amplifier, any component that goes inside of the amplifier. We try to maintain a very good return loss in the duplex filter so it matches the impedance of the amplifier. And the delay is just a measurement that we utilize. It's usually chrominance to luminance delay, which is a measurement of how much signal degradation we have at, in this case, at 258 megahertz, or the first forward channel in the forward path. So that's typically the worst case delay, but we always measure those to make sure that you don't start to get any roll off and any performance issues in that first channel that you'll be using beside the duplex filter cutoff frequencies. And onto the reverse band path. Again, all of those parameters that I just covered in the forward path are always measured, tested, and engineered to be minimal. The isolation is one of the key factors in a duplex filter, because the isolation is the point where you separate the forward and the reverse path from one another. And in a region we're going to look at on the next slide, in the crossover region of a duplex filter. Okay, so guys, this is just a spectrum analysis that shows you have, this is, in this case, it's the 5 to 204 and the 258 to 1218. So the 204 reverse is in the orange, and then the green is, of course, is in the forward path. And so we would love to build a duplex filter that had that shape to it there, which, you know, a lot of people would call that a brick wall filter. Okay, and but unfortunately, for a $20 or a $30 duplex filter, which is what we utilize in amplifiers, we cannot build a $2,000 duplex filter and expect our customers to pay thousands of dollars for an amplifier. So what you start to see is the reverse path starts to roll off a little bit. Okay, it doesn't go straight down. The filters starts to lean towards the forward path. And then if we look at the actual forward path roll off, you'll see there in the green that we have also some slow migration in filter response at that location. So guys, if you notice that, that's what we call the crossover isolation of the duplex filter. And we want to keep that as far down as we possibly can, so that we keep our reverse bandwidth in the reverse spectrum and our forward spectrum in the forward spectrum. Okay, so the crossover isolation that is typically measured on every duplex filter should be at least 40 dB down or better. We typically see 42 dB performance there, but in this case, our spec is at 40 dB down, and that allows you to keep your forward and your reverse separated. If that oscillation starts to break down, I know many years ago, I would work with sweep technicians that they would realize, hey, if I tune this air wound inductor and I move the windings around a little bit, I get a much better response. Okay, and you may have learned that way out in the field yourself, but what you're doing there is you're changing the characteristic performance of the duplex filter, where you may be looking good in one bandwidth or one location, where you're actually generating problems with the crossover oscillation, as I'm showing in this case. So you need to leave those air wound inductors or any tunable inductors in the duplex filter. You really need to leave them at the factory settings, because they've been tuned while the technician was looking at 10 to 15 different parameters. Okay. Because, and while we have this slide up, I'm sorry, Mike, can we go back? Thank you. Just one comment on those of you that may be doing a frequency conversion in the future from 42, in this case, to 204. You need to make absolutely sure that all of the signals in your forward spectrum are removed from that system before you start the upgrade process. So I've had several customers in the past few months that, you know, they forgot about that one data carrier or that one box carrier. And then when they went to the 204, 258 split, they were transmitting in that crossover region. And if you transmit a signal in that crossover region, there's a very good chance that your amplifier can oscillate, and it may be a very minimal oscillation that just simply knocks your forward MER down 3 to 4 dB. And you may not see that. So always make sure you have everything clear in that crossover region before you start a system split upgrade. Thanks, Mike. Okay, so guys, why do we need additional reverse bandwidth? Because as everybody knows, without saying here, we really need more symmetrical data in the upstream and the downstream on the cable system. And historically, the 40 or 42 megahertz has worked for us because we didn't have a lot of payload in that reverse spectrum. But nowadays, the reverse is becoming equally as important as the forward path is. And that's driven by the customer demand for the bidirectional services, whether it be gaming, a lot of work at home now after COVID. So migrating to the 204 reverse split, or even higher, that we'll cover in a few minutes, will increase that reverse spectrum and help you get closer to symmetrical upstream and downstream data. All right, guys, this is just the future of where we're heading with the 108 program. And this is just a chart that shows you, you know, what we'll be building the 1.8 gig amplifiers too. I really don't expect many people to buy a 1.8 gig amplifier with a 4254 split, but somebody probably will. So I think the more common frequency splits will be for 1.8 gig amplifiers will be the 204 258 split, or the 396 492 split, and then some customers are talking about the 492 606 split. The 684 split, all of the amplifiers will be upgradable, and they'll be field upgradable. And so you could start out theoretically with an 85108 amplifier and upgrade that in the future to 684 834 split. So over in the right-hand column, I added just a little bit of info that talks about the downstream and what. So you can see if we ever get up to the 684 split, we still have almost 1,000 megahertz of downstream signaling, similar to what many of you have today if you have a 1 gig system at 4254. But that gives you an indication of what kind of downstream bandwidth you would have with each different split.
Well, what's interesting about that is as you increase the bandwidth of the upstream, you decrease the bandwidth of the downstream.
Yep.
So I don't know that anybody likes to give away real estate or the potential for throughput. So in order for us to maintain the same amount of capacity or throughput in that diminishing downstream space, then we may have to use higher orders of modulation to maintain that same throughput capability. So an interesting little fact there. We'll talk more about later.
All right. Okay. So guys, this is just the components that you may be receiving in the future if you do an amplifier upgrade. And this is the role of the doplex filter in that reverse split upgrade. But the doplex filters would, you would be removing, say, the 4254 doplex filters and installing the 204, 258 doplex filters. And then the other four pictures show some of the other common components that have to be changed out of an amplifier to do a reverse split upgrade. And that is typically always the forward trim board, because your forward frequency is starting at a different bandwidth now. If you're going from, if you're a 4254, your 54 would be going to 258. So you cannot use the same filters and the same trim boards typically for those two frequency splits. So typically you would change out the forward trim board and the reverse trim board along with the high pass filters and the low pass filters. And the high pass filters and low pass filters are totally different than the doplex filters, but they're kind of like doplex filter helpers. They help you keep your low pass signals in the reverse spectrum and your high pass signals in your forward system. Okay, so that's just a little helper to help you keep those signals within their given confined space. Okay, so guys, anytime you're doing a reverse split upgrade, it is super important that you qualify the amp that you're upgrading, because if it's not operating correctly at 4254, chances are it will not operate correctly at 204, 258. So you need to just, before you start the upgrade process, always make sure that you verify that it's operating properly at the initial frequency split. And then when you go through the upgrade process, you know you've eliminated all the problems other than the 6 components in this case that you would be plugging into to do the split upgrade. So guys, this is just one example. Every manufacturer will be slightly different. This just, these are common parts between many manufacturers, but this is a line extender kit. If you were doing a system amp, a mini bridger like Mike showed earlier, you may very well have 3 or 4 doplex filters instead of just the 2 doplex filters, because as we know, a line extender only has 1 input and 1 output typically.
That's good information, Lynn. I think there's a misconception out there. If you wanted to do an upgrade from a sub split to a mid split or to a high split, that the only thing you have to do is change the diplex filters. Yeah. And that may not be the case.
That is correct. Yeah.
All right, let's talk about another component of amplifiers, and that would be AGCs. Okay. So guys, again, we'll just start out with some examples of the AGC. AGCs are very much like doplex filters. There's no standard for the AGCs. But there's some really good AGCs on the market today. I've got a couple of those examples here. And basically the function of the AGC, they're typically installed inside of the amplifier, and they maintain the output of the amplifier to the balance level that you would balance the amplifier, say six months ago. That AGC function is as the weather changes and the temperature either gets hotter or colder, that the AGC will correct for that loss or gain in signal. So typically as we go through the summer months in the USA anyway, and it gets hotter, the amplifier will need additional gain. So it's very important to make sure that most of these AGCs I have shown here require a back off, and the back off adjustment just simply sets the reserve gain of the module,
And that is a very key component of making this AGC work correctly. And I think Deanna's going to cover that back off and operational gain and full gain in a little bit. But basically, when we talk about operational gain, that typically includes the back off of the AGC network. So it's very important to establish that reserve gain, because as you need 2 to 3 or 4 dB more gain, you have to have somewhere to pull that gain from, okay? So most of the 1 gig and below, and even a good many of the 1.2 gig amplifiers actually have a network installed in them called the Bodie network. And the Bodie network is just a way to add and subtract attenuation. And it also has an equalization circuit built into it, or typically somewhere in that general area. So I'm going to go to the next slide and explain exactly what a Bodie network does.
Hey, before we go on to that, Lynn, here's a question. I've heard these called AGCs, ALCs, ADUs. What is the difference, or is there one?
They're pretty much the same, and I apologize. I always refer to them as AGCs, and really that's just vendor specific. The ADU that you see on the right hand side of the picture works very similar to the two that you see on the left hand side of the unit. So I think it's just the terminology differences between the manufacturers. They all serve the same function, even though some of them may serve it just a little bit differently. And we'll cover that in a few of the next slides when we talk about the Bodie. Okay, and guys, let me make sure I explain this as well, because this is just a simple drawing of a Bodie network and how it works and interacts with the AGC. First thing you need to know is not all Bodie networks are created equal, not all AGCs are created equal, not all backoffs are the same. Each manufacturer has a different requirement for their AGC or ADU design, and you need to follow the manufacturer's recommendation for balancing those modules. So don't walk away with what I'm telling you here and say that's the way we balance all of our modules, because each manufacturer can be slightly different, as each AGC is slightly different in design. Because the Bodie network itself is really just a interstage variable attenuator, and it typically has some tilt built into that network, either on the Bodie or very close to the Bodie, because when we make changes when we make corrections to the output of the amplifier for changes in temperature, that's typically, we'll use a 5 to 42 system, up to 1 gig, that's typically making changes from 54 megahertz up to 1000 megahertz, okay? So there's much more attenuation at 1 gig than there is at 54 megahertz. So we want to make sure when we correct for changes over temperature that we compensate, if we compensate 3 dB at 1 gig because of a 70-degree temperature change, we only need to correct for approximately 1 dB at 54 megahertz. So there is a tilt or a slope built into that correction network when we correct for changes over coax over temperature, okay? But as I mentioned, the Bodie network itself has the ability to add or subtract attenuation. And the way it does that is if you follow the flow from the input to the output hybrid, you'll see your signal coming into the input of the amp. The signal flows through the Bodie, and then it goes on to the output gain block, which Deanna mentioned earlier. That would be the power doubler in this case. And then at the output of the amplifier, we take a sample feed to feed to the AGC, because we want to make all the corrections to the output of the amplifier in real RF levels toward the output. Now, some manufacturers will have a conditioning pad or a control pad, and that pad is just to make sure that you have the correct levels into the AGC that will optimize the function of the AGC to its full potential. So, so typically, you know, with some manufacturers, there'll be a subtraction formula there. With other manufacturers, they'll give you a set value within a certain range of drive level. Again, follow the manufacturer's recommendation for that pad if it does have a pad location there, okay? So basically the signal then goes into the AGC, and as it goes into the AGC, that drives a DC control line. And if you notice the red dotted line going back up to the body, that is a control line that supplies a DC current and voltage to the body network, okay? So the body is an intelligent network, so as that signal starts to, what would you say, it drops by 2 dB, typically the levels going into the AGC would drop by 2 dB, but the Bodie network is intelligent enough to say, hey, I'm not satisfied with my DC voltage now, I need more DC voltage, so therefore I need to increase or decrease my attenuation and increase my RF drive level into the AGC. So the Bodie in that case would automatically take out 2 dB of attenuation so that it satisfies the voltage comparator network on that voltage, DC voltage control line. So it's intelligent enough to add attenuation and take away attenuation. There is a limit to the range that we can control an AGC and a Bodie. And in this case, in this example, it's typically about 5 dB up and 5 dB down, meaning that we could sustain a 5 dB loss in signal or a 5 dB increase in signal. And if you run the loss performance of coaxial cable and maximum spacing between runs, what you'll see is 5 dB is typically more than enough all the way up to 1.2 gig. So if you remember back to the older days when we had 400 and 450 megahertz systems, for those of you that have been around that long, we did not need an AGC at every amplifier. We could go every other amplifier, which was kind of the standard design back in those days. But when we go to 750 and above, we typically like to see an AGC in every trunk station, and at least 50% of the distribution are line extenders. And even a lot of the MSOs now have switched over to AGC in every module that they purchase, which I think is a very wise decision. The AGC just helps hold that output level, like I said, within typically about a 10 dB range. That is when it's set up correctly, okay? That means you have the correct pad installed or you followed the manufacturer's recommendation for the setup of this AGC. So you can set these up incorrectly. You can put the incorrect drive level pad in. You can not perform the back off of the Bodie network or the manual back off, which means you will not have any reserve gain when you need it when it gets hot in the summer months. So again, follow the manufacturer step by step for setting up these amplifiers and AGCs. I'm just trying to cover a little bit of the overview of how it works. So let's get into a little bit more detail with some of the medium advanced AGCs, okay? This is basically an AGC that has a loss of pilot feature built into it or associated with the AGC. So if you look at this drawing closely, you'll see that there's the signal coming from the directional coupler was the same directional coupler that we had on the previous page. The drop-in pad is the same conditioning pad that we covered that you would see your manufacturer. In the case of this AGC, we're typically trying to get 8 dBmV into this AGC at 711, 609, 499, whatever your pilot frequency is, okay? So 8 dB is the correct drive level into this AGC. And from there, it goes straight into a variable attenuator, and that basically is a 9 dB adjustment attenuator that when you're setting the gain of the AGC, that's the potentiometer that you're turning, okay? So the biggest point I want to make on this slide is some of these AGCs, not all of them, have a loss of pilot feature. So if we go down to where the arrows on the right-hand side are, that is basically a switch that will keep the AGC in the AGC operating mode. Okay, that is a voltage control switch. When the voltage of that switch gets out of its operating range, it will automatically switch to the overhead thermal position instead of driving the amplifier all the way to max gain. So when that level changes on the input, if you remember, we had 8 dB into the AGC. When that level changes approximately 8 to 10 dB, there will not be enough voltage to drive that voltage control switch. So the AGC would automatically switch out and kick into the overhead thermal position. Now guys, not all AGCs have this loss of pilot feature, and not all AGCs have the same design in the loss of pilot feature. This is just an easy one to give an example of because it's very visual, and it shows you how that switch works. If you guys remember the old AB switches we had years ago, you can think of that voltage control switch just like an AB switch. It's currently in the A position shown in the drawing, and when the voltage goes beyond its rated, it would switch over to the B side, which would become the overhead thermal position. But again, those are things you need to check with your manufacturer with, because not all AGCs have a loss of pilot features, and some of them have a different loss of pilot function, okay, that doesn't trigger at 8 to 10 dB of less signal loss. Okay. So guys, let's talk about where we're going with AGCs, because what we've talked about so far is traditional AGCs that are Bodie based, and probably most all amplifiers built in the past 25 to 30 years had a Bodie network in them of some sort, and we've advanced that over the years. The Bodie networks today are much better than the Bodie networks 15 or 20 years ago, or maybe 30 years ago. Okay, so but I still expect the traditional Bodie-based AGCs to be around for a long time. They work very good up to 1.2 gig. They're very functional. They're great when they are set up correctly. Okay, and that is typically a traditional Bodies or traditional AGCs. I would say would have a fixed filter in them, meaning that they're a fixed frequency. There are some AGCs on the market today, and a couple of different manufacturers utilize a frequency agile AGC that you can actually select the AGC frequency, and you can change the AGC frequency as needed. So going forward to 1.8 gig and where we're going today, what we're seeing is the Bodie-based network may not work to cover the spectrum all the way from 54 to 1.8 gig, 54 megahertz to 1.8 gig. So we have to develop a new technology for 1.8 gig amplifiers, because in most cases the Bodie concept will not work at 1.8. So most of the newer 1.8 gig modules, and probably some of the 1.2 modules, they'll incorporate a much more advanced software-driven technology. And so basically, if you need to change the drive levels, the frequency of the AGC, that'll all be programmable through a microcontroller or a microprocessor and through software commands going forward, instead of having to make those physical changes out in the field. So if you wanted to go from a 609 AGC to a 711 AGC, you would physically have to go out in the field and remove that AGC and/or program the AGC. And in this case, you'll be able to do that remotely by connecting to the microcontroller and selecting that from a pull-down table. So if you wanted to go from 711 to an AGC at 1002 megahertz, you just simply pull that up in the software program, select it, execute it, and then you've changed your AGC frequency at that point. Okay. Now, typically, at least where it stands now with 1.8 gig and that software, you'll be able to either connect to it locally with a direct USB interface, or possibly even a Bluetooth or Wi-Fi. And then also in the future, you'll be able to make that change from your office through a status monitoring application. Okay, so if you have a status monitoring device in that amplifier, you would be able to log into that status monitoring and change your output levels, as well as your potentially your AGC frequency. And again, not all amplifiers will be created equally there. So as the 1.8 gig amplifiers start to come on the market, again, talk with your manufacturer, make sure you have a clear understanding of what the options are. So guys, if you have not had a chance to read SCT 279, it's a great standard, and it will tell you a lot about how the future of AGCs will work. So if you don't have a copy of that, make sure you go to the SCT website, download a copy, and read through it. It is very informative.
Thank you, Lynn. That was a lot of great information on AGCs and AGCs of the future. Okay, up next, we're going to talk about some of the key RF amplifier parameters. Deanna, let's talk about gain.
Let's talk about gain. So as Lynn mentioned already, it's really important parameter to determine how effectively the amplifier is boosting the signal or increasing the signal while maintaining quality. There is like a few operational gain. There's a few terms in terms of gain. Max gain is the one that the amplifier can provide without any backup. Is the maximum strength or amplitude the RF signals are going to get through the amplifier. That max gain, it's accessible on some of the amplifiers and needs to be really and you need to optimize it based on the manufacturer requirements to be able to have enough backup, like Lynn mentioned, for the AGC control. And then the one that we refer to the most is the operational gain, because it already takes into account that backup or reserve gain to accommodate for AGC, ASLC, ADU, any type of thermal compensation. And then on the axial ports, that's a different type of gain, and is the gain that is actually driven by what kind of plugin you put on the aux port. If you put a DC, if you put a splitter, all the gain is going to be affected on those auxiliary ports based on the insertion laws, like Mike mentioned. So just make sure that you check the specs on the plugins when you're taking into account your output levels to be able to make sure that you're using the right gain.
Another important thing to understand about your amplifier is the noise figure. What is the noise figure exactly?
So yeah, noise figure in amplifiers is a system parameter that characterizes the ability to process low signals. In HFC, we think it's sometimes we call, oh yeah, we have a lot of TCP, but in reality, the signals that are processed by the amplifier is still low, and they're really susceptible to noise. So noise figure is often a key parameter that differentiates one amplifier from another to see how clean the amplifier can boost that signal. For example, an ideal amplifier will amplify the noise and its output with the signal, right? Maintaining the signal to noise ratio at the input and at the output the same. But in reality, amplifiers also add some extra noise because of the circuits internal to the amplifier. We don't have the semiconductors, the gain blocks, everything introduces a little bit of noise that degrades the signal to noise ratio of the signal. That is why so low noise figure means that very little noise is added by the network or the amplifier. In HFC networks, we increase the ratio of signal level to noise level to effectively transmit that data. Since we transport lower signals, like we mentioned before, in practice, if the signal falls below that noise, then they call the noise floor in the amplifier, then the data can no longer be decoded by the cable modem or the receiver, which is our end device. affecting the quality of the service. As we see in this example, the input signal and the noise floor, which is the red line, increase as it passes through the amplifier, increases both. The gain also amplifies the noise and the signal, and that's something we need to keep in mind. That's why it is so important to ensure that the client is clean, and that there is no any other impairments to avoid amplifying the noise and compromising the quality of the signal.
Very good. Let's talk about the return performance of the amplifiers next.
Yes, so amplifiers are not perfectly linear, like we mentioned. So this means that if we plot output voltage versus input voltage of an amplifier, or the input levels versus the output levels, we won't see a straight line. There are non-linearities introduced by the semiconductors of the gain blocks, and the effects due to the saturation effect of the amplifier operating close to the crash point. In the forward, we do that on purpose to be able to maximize the gain and the distance, and to be able to keep as much as possible the latency spacing. When modulated signals pass through the amplifier, these signals are subject to distortion. As these products are generated, they look like noise-like because we're using digital signals. These products are known as intermodulations or products. It is really important to understand these limitations because as we develop high capacity, complex broadband amplifiers, as we are seeing, they're getting more and more complicated, the performance is really crucial. Clearly understanding of the TCP limitations is one of the points. Then this is also really important for design decisions around the HFC network and for operations. So why do we use noise power ratio to characterize amplifiers? So noise power ratio is a tool to help us better understand the RF amplifier performance. And it's a tool that helps us measure the intermodulation distortion, capturing the accumulated distortions from text signals across a variable range of input levels in the amplifier. This helps us understand the total composite power limitations of the amplifier or active devices like nodes as well.
So it's interesting that NPR, noise power ratio, as you mentioned, isn't new. But I think it's only fairly recently that we've started talking about it in the context of amplifiers in the either upstream or downstream direction. I remember years and years ago when I first heard of an NPR curve, it was in the context of the return transmitter in the node to the receiver back in the head end. So the management of the NPR curve was really a head end and an optical tech problem. But now, with some of these higher TCP systems and wider bandwidths, I think NPR is really relevant to amplifiers and RF beyond the node. So that's a bit new maybe for some of our audience. When we're talking about NPR, we're not talking about optics, we're talking about amplifiers.
Yeah, like you mentioned, NPR is a really important tool that it's been around for a while, but it's been used mostly in the labs to be able to qualify the performance of different actives and optical devices. But we can see a straight correlation with NPR and MER curves. And MER curves are more the tool that is used by the technicians. So NPR is kind of like that gateway to get you to use the MER curves to see any potential signal qualities that are being introduced by the amplifier or any active device or optical device in the system. But also it helps us understand, these plots are so important to us because it helps us understand how we can optimize these active devices to be able to maintain the quality signal. So then with the NPR by itself, we use the curves that this produces, and it represents the RF output profile of any active. in a range of different input levels. And these MPR plots have different regions that we're going to go through. The first one is the noise region, and is when you have really low inputs, and is represented on the left side of the curve. And it increases approximately 1-to-1 ratio as the input power increases. There is where the power in the notch, or like when we measure it, is where the power is dominated almost by thermal noise. So if your inputs are way too low, your thermal noise takes over, and that's why you have low quality signals. As we go up in the curve, we go to the intermodulation region, and as the top of the curve, and it's where it starts to round. This area is where everything is dominated, start to get dominated by intermodulation noise or products. This is where the amplifiers need to be, when we pick a region in this area, to be able to optimize the amplifier, and then usually we call it the target MPR. And that's to select an input level that gives you an expected performance based on your needs. Since all HFC networks are different, this is gonna be different for each operator. So it is important just to recognize that you have the intermodulation region, because that's where you're gonna select your optimal target input level. Then as we go up the curve, we start getting in the downhill on the clipping region. This is when the maximum input level or TCP levels are reached at the amplifier, and then the amplifier starts getting into saturation. The clipping region appears where all the amplifier is affected by high order modulations or products. In this region, the MPR curve really, since we're using digital signals, you're going to see this effect even higher. It's really stiff, so it really goes down quick. So since this area determines the performance of the amplifier, any ingress, any little increase of signal is going to drop your performance by a significant amount, up to 10, 12, 15 dB.
So it's interesting that you mention that, right? Because in the noise region, you mentioned that it's approximately 1-to-1 relationship, right? A linear relationship. As your signal increases, your noise power improves.
Right.
Until you get into this nonlinear region over here, where a 1 dB increase may result in multiple dB of distortion.
Right.
I think it's also important to note in this particular chart, these are specific to amplifiers. Because in the horizontal axis, we have the input levels in dBmV per 6.4 megahertz upstream channel. So every amplifier might be a little bit different, right?
Right, exactly. And that's a really good point. That's why it is important that you sync up with your operation teams and your vendors to be able to make sure that you're using a target input reverse level that is being determined by these MPR curves, because every operator has different dynamic range desires. And what is dynamic range? Is selected based on the target MPR that the operator needs to supply. So if have more dynamic range in the return is important, because we have enough margin for the return amplifier to tolerate additional energy before going into that clipping region. In other words, if we leave some margin, this allows us to have some tolerance for ingress and impulse noise that won't be able to make the amplifier go to the clipping region. The same effect works with the optical devices. It's just that the input levels are gonna be completely different than the ones that we're showing in this graph as well. So on the next one, the other point that I wanted to make is that as the number of digital signals increases as we go to mid-split or high-split, the input level profile and the distortions generated, as I mentioned, they look like noise-like characteristics. This noise plus distortion accumulation effect at higher bandwidths can be visualized on MPR plots. So for example, on the blue line, we can see that for low split or subsplit, we can have a higher dynamic range because we need less channels, so that we can actually have higher input levels. But as we increase the bandwidth, the noise plus distortion accumulation increases as well. And this decreases the MPR curve, making it the amplifier to crash sooner. And this also, the effect is that you need to lower your input levels to keep the same performance, and you have less dynamic range. That's why it's so important as we go up in different high split, low, mid split, to be able to sync with your team and the manufacturer to select the recommended target input level for certain MER performance. This is really important because this will allow us to lower distortions on the hybrid, and also is key because this will be determined by the design. So all these parameters are really important for the network, because as we can see, if we run at sub-split at 18, in high split, that's actually past, we're already at the crashing zone. So any ingress will make the amplifier go down, or the laser in that case. And the next one, the other effect that MPR has is that when we optimize the nodes, for example, from low split to high split, cable modems haven't changed. Their TCP is still the same. So that's why we need to reduce the power levels per 6.4 megahertz carrier. I put it in this case. And they need to be reduced by 7 dB to around 7 dB to be able to accommodate high 204 megahertz bandwidth. The cable modem transmit power level remains the same. That means that for high split, that power needs to be distributed across way more channels than for low split, as we illustrated here. So that's the other effect of why that lower input reverse is so important in high split.
So that's an interesting concept that I don't know that we all fully appreciate, is that the modem is only capable of transmitting so much power, total power. But the more bandwidth that it's able to use, that power has to be distributed across the entire portion of the available spectrum. So the amplitude can't be as high in order to achieve the same power. So effectively, if we look at this, we can say this 65 TCP of one channel is really the same as the TCP of these 30 channels. It's just distributed across a wider spectrum.
Exactly,
so power,
and that's why you're
amplitude.
Yeah, exactly. Power TCP is your limitation in any active device. So if you keep the same per channel level, you're gonna crash that device as you go higher in bandwidth and you add channels. Like you mentioned here, before, if we just had the modem transmitted one 6.4 megahertz channel, then we would be able to transmit at 65 dBmb. But in low split, that's why our max per channel power was 57. But as we go to high split, that per channel power goes down to 50.
And I think that's really important to understand as we get into the setting up of your return path, particularly with respect to your drive levels, right?
Exactly.
So we'll introduce sort of the drive level conversation here. And that's basically your input power into the port minus any losses incurred between the port input in the first gain stage. So in the return, that's typically measured as dBmV per channel, right? So we would say we want 18 dBmV at the port. That would give us, in this instance, 48 on our DOCSIS transmit level at this test point, or at this test point. But the actual input level to the hybrid has to consider any insertion losses of a signal director plus the input attenuator, and that actual drive level then is different than what the port input level is. And then our output level would be the drive level plus the operational gain minus the insertion losses of our equalizers and attenuators. And as Lynn mentioned, even diplex filters have a little insertion loss. So where we measure that on the output, our output level is the sum and subtraction of all of those individual gains and losses in the return. So that's the return. Let's talk about the forward and some things to consider when we're setting up the forward portion of our amplifiers. Very similar to the return, the forward concept is very similar. We have our input level, typically measured in dBmV per channel, and referenced to a high pilot and a low pilot or balancing carriers as measured at the test point on the input of the amplifier. However, that test point is often before the diplex filter and the input pad and equalizer stations. So when we're calculating the drive level to determine our NPR or MER curve performance, we actually have to do the math and subtract the losses of our input attenuator and equalizer to measure the power per channel at the first gain stage, or our total composite power. Then we'll, as we mentioned, some of the more modern amplifiers have 2, 3, 4 gain stages with AGCs and BODIs and other trim networks and internal equalizers. So all of those have to be considered in order to calculate our output level. So our output level is our drive level plus the operational gain minus internal passive losses. And we typically measure that on the output test point, which is after the diplex filter, which may also have insertion loss, and is typically measured in high and low reference or balancing carriers. So as we described, we need to differentiate a little bit between our input level and between our drive level, because one could argue, and I will argue, that the drive level is the more important of those figures. That determines the placement on the NPR or MER curve, and ultimately the signal quality performance of the amplifier. As we discussed in the upstream portion, there's an NPR curve for the downstream also. So in this particular example, the noise power is in the vertical axis, and it's measured in the horizontal axis with total composite power. Now, in the outside plant networks, we don't measure the amplifier is in total composite power. We measure it in dBmV per channel with specific channels. So something called an MER curve might be a little more easy to understand where the performance of the amplifier is concerned with the drive level and the signal quality. So why are NPR curves important? As we mentioned before, we're going wider and wider in our upstream bandwidths, but we're also going wider in our downstream bandwidths, as Lynn mentioned earlier. And since attenuation is a function of frequency, the higher frequency we transmit signals in, the more attenuation there is at those frequencies. Therefore, we need more equalization and more gain to achieve unity gain in the downstream direction as well. So all else being equal, the higher the frequency of signals you're transmitting, the more gain you need in your amplifiers. And with more gain comes more risk. Here's an example of some MER curves that were constructed by our engineering and lab teams to understand the performance of the amplifiers with respect to the drive level. Again, the drive level being the input level minus the pad and equalizer value, that's the level into the first gain stage. So in this particular amplifier, as the input signal level per channel increases in the drive level, this would be the noise region that Deanna mentioned earlier that's fairly linear, whereas you increase the power, the noise performance improves, in this case the MER, until you reach that intermodulation region where it starts to flatten out, and then into the clipping region where the more input level you have into your amplifier, the more distortion it's going to create in a nonlinear relationship. So at this point here, this would be the clipping region. I think we've all seen in history class when we were in school, those ancient maps, right? Where there was a land mass and then the ocean, and out in the ocean, there was a symbol that says, "Here be dragons," right? To discourage people from going there. You don't want to go out into the middle of the ocean where the dragons are. Well, on the MER curve, here be dragons. We don't want to go here because bad things happen. So the more signal that you put into the amplifier, the better the signal quality becomes until you get into the nonlinear or the clipping region, at which point the distortions increase in a nonlinear fashion. So this does vary by amplifier type and model. In this particular amplifier, after we get over about 11 to 12 dBmV per channel, we start to see that's where this clipping region starts to happen. But in a different amplifier model, that clipping region may start at 16 or 17 dBmV per channel. So it very much depends on the amplifier model and how many channels or what the total composite power of your system is. If you were to add more channels to this channel lineup in the same amplifier, this clipping region may shift to the left because there's more total composite power. So it's very important when you're developing an MER curve to understand the make and the model and the performance of your particular amplifier and how many channels are in your channel plan. So why is it important? Again, in order to properly set up your amplifier so that it doesn't go into the distortion region or it's not operating in the noise region, you need to understand the drive level and also the MER curve of your amplifier. So let's do a little input exercise. We've already looked at an example of an MER curve. So let's imagine that we have an amplifier where the target drive level is 6 dBmV per channel. We have a 750 megahertz channel lineup, and our input levels are 12/19. So if our input levels are 12/19 and our drive level, the pad should be a 6 pad, right? That's easy math. Well, no. Because what we didn't do was recognize that the equalizers also have loss. Equalizers, as I mentioned, are frequency-specific attenuators. So an equalizer has loss, but different loss at different frequencies. So I have this little calculator that allows me to put in my input channels. In this case, channel 117/198. Those are my balancing channels, and I have 12/19 coming in. I would need to install a 12 value equalizer in order to take that tilt and flatten it out going into the drive level of my amplifier. Now, if I look at a 12 value EQ over here, I actually have 4.3 dB of loss at 750. That's the insertion loss of the equalizer at that channel. And at channel 98, I have about 11.6 dB of insertion loss on that channel. So I have to subtract that from my actual input to get the drive level, not including my input pad. So in this instance, with an input pad value of 2 and an input equalizer of 12, my drive level is actually a flat 5. So that would put me at a really close to the target input level or drive level of this particular amplifier. So I've talked to a lot of technicians, and quite frankly, I've done this myself, where we don't appreciate the losses contributed by the equalizers, and we end up underdriving the amplifier, which means that the amplifier is actually operating in the noise region, not in the ideal intermodulation region of the curve. So what happens if you get it wrong? As I mentioned, here be dragons. And this is actually a great example of an amplifier that was set up in the clipping region of the curve. So in this example, the technician that set this amplifier up, it was a very new amplifier series, and he didn't have a huge selection of pads and equalizers to set the amplifier up. Now, he needed 16 dB of total attenuation in the amplifier in order to get his output based on the operational gain and the input. Now, he had a 16 pad, and the amplifier came pre-stuffed with a jumper. So he had a choice. I can put the 16 pad on the input of the amplifier, or I can put it on the interstage or the output of the amplifier. Well, in this case, he chose to put it on the output. Well, this was a second amplifier in cascade. It was a relatively short amp spacing. So there was a lot of RF coming into the amplifier. Well, what happened was, having a 0 pad on the input of the amplifier, his drive level was in the clipping region of the amplifier's NPR curve. So while his output levels were exactly correct, his signal quality was very low. There was 31 dB MER on the output of the amplifier, even though the amplitude of his balancing carriers were exactly correct. So what we did was took 10 dB of output attenuation from the interstage and put it on the input. And what that did was move back into a linear intermodulation region of the amplifier, and the MER improved by 12 dB. So that's why the input drive level is so important, is because it can actually affect the signal quality of the amplifier itself. Now, in both of these instances, the total station attenuation was the same. The operational gain was the same. The amplitude or the output level of the amplifier was the same. But the big difference was the signal quality because of the position of the first gain stage on the NPR curve or MER curve. So when properly set up, today's amplifiers are very high quality. They're capable of passing very high quality signals through them, but setup is so important. Now, on the output side of this amplifier, we have the ability to pull some information from video set-top boxes and cable modems, right? This was an example of an amplifier that was operating in a nonlinear state due to temperature and an AGC not being properly set up. So it got cold, the amplifier's AGC was not turned on, and the output signal levels increased dramatically, which also increased the drive level to the next amplifier in cascade, putting it into a nonlinear performance region. So we saw high output levels and very poor signal quality. So in this instance, you can see this orange trace is a full band capture of a modem that is running at very high output levels. But out here in this vacant portion of the spectrum, you also see there's a lot of noise, or what looks like noise, but is actually second and third order distortions because this amplifier is operating in a nonlinear state. Now the green trace is the same modem after the amplifiers were set up properly and the ADU was set up. So you can see that the total power went down, but the noise floor went also way down because those distortions were no longer there. So in this instance, the signal quality improved significantly because the amplifiers were set up and the AGCs were set up correctly. Okay, we're almost done. Deanna, remind us why this matters.
Yeah, so as we can see, RF amplifiers have evolved, they're getting complicated, and even though they're really resilient and they provide incredible performance, we need to be diligent in setting them up properly so we can provide reliable high-speed internet services to our business and homes in our network. These critical components enhance not only the strength of the signal, but they need to maintain quality. But this quality is dependable on how well we set them up. So just remember, it is crucial to optimize them based on guidance that are joined between the network operators and the vendor community.
As we mentioned, in order to achieve higher speeds in bandwidth limited systems, we may have to offer higher order modulation. And these higher orders of modulation, like 4096 QAM, require much higher signal quality than some of the legacy channels like 256 QAM. So in the future, signal quality equals throughput, which equals speeds. So it's critically important that we properly align our amplifiers to maintain the highest quality signals to offer the greatest speed to our customers. So with that, we actually do have a few questions. Lynn, the first one is for you from Sean Mondoro. Looking at trim boards and equalizers, what will the future of amplifier response balancing be like as we look to increase the total bandwidth of the spectrum while shortening the spacing? Will we see more linear equalizers used in place of cable equalizers to help with the response?
Okay. I'll take the last question first. I don't expect linear equalizers in the input, but definitely in the interstage there is a chance you may see more linear equalization in the interstage, because the input equalizer actually takes care of the cable curvature in a lot of amps, and then at that point it actually can be considered to be a linear interstage in some cases. And so I've talked to customers that go both ways with that. Some want linear, some want cable, some want a combination of linear and cable. All right. And then as far as the sweeping on the response networks, when we get to 1.8 or even at 1.2, there will probably be a little bit more limited access to the response boards, because especially in the 1.8 gig modules, it is extremely difficult or prohibited almost to put a lot of openings in the cover. The more openings you put in, the more problems you're going to have. You're going to see more of a solid cover with probably casted lid covers that shield the RF between the forward and the reverse path for better oscillation. So sweeping in the future may be a little bit more difficult, where historically people have gone out and just tuned the cap or tuned a resistor to improve their performance and the return. That may be more of a challenge going forward.
Very good. Thank you, Lynn. Deanna, I think this one might be for you. Everything we've seen here today is based on the input levels of the amplifier, which makes sense, but most of us utilize unity gain based on balancing our output levels. Is this the wrong way to balance our amps?
No, unity gain is still really important, and we are keeping that into consideration during this setup. So when you're balancing to keep the same output levels, the important part to be cognizant of is the drive level that Mike mentioned. So once you set that up and you keep the standard output levels, you maintain unity gain. And in the upstream, once you always hit that port, reverse input port at the target level, let's say 18 or 13 or whatever is set by the design print or by your operator, that will maintain in the upstream as well. Just make sure that the injection is flat. So do your lower and your higher frequency set at the same target input reverse. Otherwise, you are going to mess up the unity gain.
I think what I hear in the question is maybe some of the old knowledge suggested that you didn't use the interstage pad to set up your amplifiers. You did all of your padding either in the front on the forward or on the output in the return. And I think what we were trying to say today is the drive level is critically important in both the forward and the return directions. So that means more padding may have to be done in the interstage locations, which isn't necessarily common for some techs in their unity gain models. So it's a good question, Chad. I think the answer is both. Drive level is important, and the use of the interstage padding in the forward and return is also important.
Yeah, let me add something there, Mike, too, because this is one thing I do in my travels as I go out and look at the operating levels of each system. It is easy to calculate the interstage pad value. So if you're reducing the gain of the amplifier, and some systems have to do that, but if you ever reduce the gain of the amplifier, you can go through a calculation that determines what interstage pad value you may need in every amplifier. So if you determine that you have you need to put in 4 dB of interstage padding because you're lowering the gain of the amplifier because you're running 6 dB lower than the recommended spec sheet standard, that is the pad that should go in every location if you determine that that's going to be your balancing level throughout the system. And we do that a lot. We add interstage padding. Typically, it's only 2 or 3 dB, and but that helps the performance of the amp because then you're not starving the input of the amp or overdriving the input of the amp.
Yeah, thanks for that, Lynn. Hey, we have one more question, and Lynn, this one's for you as well. Got a stumper here from my friend Nick Segura out in Rocky Mountain and Charter. So here's the question. In a high split 204 megahertz architecture, I would like to insert a 500 kilohertz forward sweep telemetry signal at 256 megahertz, which is 2 megahertz left of the diplex edge. Can this work in an amplifier cascade of 6 of your amplifiers?
And the answer would be yes, but I do caution people going out of band. I've also had to troubleshoot some other issues with that out of band frequency, just barely out of the band edge. You've got to be careful that you don't turn up the amplitude of that carrier so much that it starts to interfere with the crossover oscillation of the diplex filter in the amplifier. We have troubleshot some systems where we recorded that telemetry level in this case at 60 dB because they could not see it out in the field because of the roll off of the filters, and they kept turning the carrier up so that they could see the levels out in the field. So just be careful that you don't overdrive that level.
Awesome. Well, that's all the questions that we have in the chat. I don't see any hands up. So I do want to say, first of all, to our panelists, Deanna, Lynn, thank you so much. Appreciate you volunteering your time and expertise to this webinar. And to our panelists and our guests, we hope you found this informative and entertaining. But I also want to shout out all of the chapters that participated and advertised this section, including the Rocky Mountain chapter, the Chattahoochee chapter, Penn, Ohio, the Dixie chapter, the Great Lakes chapter, folks all over the country that tuned in today. Thank you for joining, and thank you for your support. And Deanna and Lynn, thank you. It's a pleasure as always, and appreciate your partnership today.
And thank you, Mike, for putting everything together. You did a great job.
Yeah, thank you, Mike. It was an honor to be here.
Awesome. So this video will be recorded and it will be made available through the Penn, Ohio SET chapter website, and we're also intending to make this available on YouTube as well. So stay tuned for that. Okay, folks, thank you all for your time today. Until next time we see each other, stay safe out there on purpose.
Thank you.
Thank you.